Hello, welcome to another module in this MOOC on CDMA, MIMO and OFDM wireless communication system. So in the last module, we had seen the motivation, or we had basically seen how these wireless communication technologies, that is MIMO, CDMA and OFDM technologies, have enhanced the data rates and reliability across different generations of wireless communication systems. So now let us start our study of these communication systems. So to understand the motivation behind this, let us first start by understanding the challenges in the context of wireless communication system. So what are the challenges for So what are the challenges for wireless communication system? That is, let us say we have a typical wireless communication scenario with a base station mounted on the top of a tower. So this is my base station or my transmitter, and I also have my mobile station or my mobile, which is at the user. And when the transmitter, and this is also, let us consider a downlink scenario in which the base station, this is transmitting and this is my receiver. And of course, when the base station is transmitting, typically what I have is I have the signal which propagates and reaches the mobile. So this is the signal which is propagating from the base station, or the signal path which is propagating in a straight line from the transmitter to the mobile. However, in a wireless communication scenario, unlike a wireline channel, there is no guiding medium, there is no wire between the transmitter and receiver. So while there is a straight line path between the transmitter and receiver, there can also be multiple reflected components which arise from, for instance, objects such as trees. So these are some trees in the wireless propagation environment, and you can also have some other objects which deflect the signal, for instance, such as buildings. These are my So there are trees, there are buildings, and these, what these are doing is these are deflecting, or these are scattering the received wireless signal. Therefore, these are also known as scatterers. So these trees and buildings, they are known as scatterers, which scatter the wireless signal, as a result of which you have not only the straight line component, but also you have these multipath components, these components which are arising from the scattering action of the scatterers, that is the trees and the buildings in the wireless propagation environment. So what you have at the receiver, if you can see this, what you have at the receiver is multiple signal components. So you have multiple signal components at the receiver. This component, which is the straight line component, is known as the line of LOS, or the line of sight, component. These components which arise from the scattering action and which basically are the deflected components, these are known as NLOS, or the non-line of sight. These are known as the non-line of sight component. So we have a propagation environment, wireless propagation environment, in which there is a line of sight path between the transmitter and receiver, and also there are multiple non-line of sight components, and together what we have is therefore multiple signal components at the receiver, and therefore this is also known as a multipath propagation environment. The wireless communication environment, the fundamental aspect of the wireless communication environment is that it is a multipath propagation environment. So this is a multipath propagation So this is a multipath propagation environment, and therefore what we have in this multipath propagation environment is we have the superposition of these multiple radio waves or these multiple electromagnetic waves or these multiple radio signals. So this multipath propagation environment, this leads to superposition This leads to the superposition of multiple signals. As a result, now we know from our basic knowledge of physics that when these multiple electromagnetic signals interfere or superpose with each other, they basically interfere, and that can lead to interference which is either constructive in nature or destructive in nature. So this leads to first interference, and this interference can either be constructive interference or this leads to interference which is either constructive or destructive. If the interference is constructive, that enhances the signal amplitude. If the interference is destructive, then that basically attenuates the signal. So when we have constructive interference, so constructive interference amplifies constructive signal amplifies received signal amplitude. Destructive interference this therefore attenuates So the destructive interference attenuates the received signal amplitude. So this leads to an interference environment. The multipath signal propagation wireless environment leads to interference of these multiple signals at the receiver, which if it is good can be constructive in nature, this constructive interference which enhances the signal strength, but also it can be bad, that is when it is destructive or destructive interference which leads to an attenuation of the received signal. So what we would do, what we would like to do is we would like to develop a model for this multipath propagation environment. So our aim is to develop a model for this multipath propagation environment to therefore understand this wireless propagation environment better. So we would like to develop a model for this multipath propagation scenario. And how do we develop for the model for this multipath propagation environment? When we talk about a model in the context of engineering or communications, we are talking about an input or output system. So let's say we have a signal xt which is input to my signal to my wireless system, and this is my output signal. So this is my input signal, and this is the output signal, and this is my wireless environment or my wireless channel between the transmitter and receiver. We would like to develop a model for the response of this system, that is HT is the impulse response of this system. We would like to develop a model for the response of this system. This is also known as the wireless channel. This is HT, that is what is the relation between the transmitted signal and the received signal, that is transmitted signal XT and the received signal YT. To know that, it is important or extremely important rather to basically develop a model for this wireless channel, the intermediate wireless channel HT, and once we develop a model for HT, then knowing the transmitted signal XT, one can basically get an idea or one can derive the received signal YT. Now, therefore, we would like to develop a model for this impulse response of the channel, wireless channel, that is HT. And now we can observe from the wireless environment that it is a multipath propagation environment, and each path is characterized by two aspects. One is the delay because of the propagation, the other is the attenuation which is arising from the scattering. So, each path, so let us say there are L paths, the ith path of the wireless environment is characterized by a delay, that is tau of I, and then attenuation that is A of I. Right. So, each ith path in this wireless communication system is characterized by the delay of the signal which is tau of I and the attenuation which is A of I. And from the perspective of signals, we can represent a delay, a system with a delay can be modeled as delta of the response of a signal which delays a signal by tau of I can be modeled as delta tau minus tau I, where delta is the Dirac delta function, or this is the impulse which is shifted by tau I, and this is therefore multiplied by AI, which is the attenuation. So, this is AI which is the attenuation, this is multiplied by the impulse, the shifted impulse delta t minus tau I. Now, this represents a system, that is AI delta t minus tau I represents the system which attenuates the signal by AI and delays it by tau I. And therefore, now if we have a system which has L multipath components from 0 to L minus 1. So, we have a system, we have a multipath scenario with L components, that is 0, 1, so on up to L minus 1. And for instance, the 0th path is associated with attenuation A naught, delay tau naught. The first path is associated with attenuation A1, delay tau 1, so on up to L minus 1th path is associated with delay AL minus 1 and attenuation AL minus 1, and this gives rise to the channel for the 0th path, which can be modeled as we have seen the attenuation A naught, the impulse delta shifted by tau naught, the attenuation A1, the impulse shifted by tau 1, the attenuation AL minus 1, impulse shifted by tau L minus 1, that is the delay corresponding to the L minus 1th path. And now, what we will see, so this is the 0th path, first path, and the L minus 1th path, and the multipath impulse response is basically the sum of all these components. So, our multipath channel response because remember the received signal is a superposition of all the signal components. Therefore, the multipath channel response h of t is a sum of all these individual responses corresponding to the individual components. So, the multipath response equals sum implies my response h of t equals a naught delta t minus tau naught plus a1 delta t minus tau 1 plus so on up to al minus 1 delta t minus tau l minus 1, which can be succinctly written as the summation ai delta t minus tau I going from 0 to L minus 1. Therefore, now what we have done is we have now developed a model for this intermediate channel, that is the response of the channel Ht in terms of the attenuations of the paths and the delays of the paths. And what we are saying is this response h of t is equal to summation I equal to 0 to L minus 1 ai delta t minus tau I. So, this is the response of the channel, this is the impulse response of the channel. Alright. So, what we have done is we have been successful in developing a impulse response of the channel, that is how to model the channel between the transmitter and receiver for this multipath wireless propagation environment. Now, let us look at the transmitted signal in the wireless communication signal system. The transmitted signal can be written as follows, what we call as a passband signal Sp of t equals the real part of the summation, or Sp of t is simply the real part of S of t times e to the power of j 2 pi Fc t, right. So, this signal S of t is our complex, this is termed as the complex baseband signal. This is up converted to a carrier frequency Fc, and this is transmitted over the air, right. This is transmitted over the radio propagation channel. So, Fc is basically, this basically denotes the carrier, and e to the power of j 2 pi Fc t denotes the modulation with the carrier frequency. So, Fc denotes the carrier frequency, St is the complex baseband signal, and this Spt, this is termed as the passband signal. So, I have Spt, which is the passband transmitted signal, is basically the real part of the baseband, complex baseband signal St times e to the power of j 2 pi Fct, which represents modulation by the carrier at carrier frequency Fc. For instance, and this carrier frequency plays an important role in wireless communication system. For instance, Fc is approximately equal to, for instance, several countries operate GSM in the 900 megahertz band, and for 3G, for instance, for 3G Fc is approximately equal to 2.1 gigahertz, that is 2.1 gigahertz band, and for 4G this is equal to 2.5 gigahertz band, and of course these bands are not fixed, these bands vary from country to country depending on the frequency bands allocated in that particular country, that particular region. All right. So these are a rough indication of the different bands that can, for instance are allocated in some of the major countries across the world for these various wireless communication systems. And therefore what we have is that when this communication signal SPT is transmitted, that is this passband signal is transmitted across the multipath communication channel, we have the different multipath components. Of course, the component 0 is going to, for instance, we have looked at this previously, that is the 0th path. This corresponds to attenuation by A naught and delay by tau naught. Therefore, which means the signal corresponding to the 0th path is basically the signal which is attenuated by A naught and delayed by t tau naught, that is S of t minus tau naught e to the power of j 2 pi f c t minus tau naught. So what we have is basically we have the 0th path which corresponds to attenuation by A naught and delay by tau naught. Therefore, the passband signal is basically attenuated by A naught and delayed by tau naught. So therefore, I have the received passband signal corresponding to this component is given as A naught S of t minus tau naught e to the power of j 2 pi f c t minus tau naught. Similarly, for the first path, which corresponds to A1 and attenuation by tau 1, the received signal is A1 times S of t minus tau 1 e to the power of j 2 pi f c t minus tau 1. And so on and so forth, we have L paths. So the L minus 1th component from counting from 0, that is so L minus 1th path, which corresponds to attenuation A L minus 1, delay tau L minus 1, that will give rise to the components A. So that will give rise to the passband signal A L minus 1 S of t minus tau L minus 1 times e to the power of j 2 pi f c t minus tau L minus 1. So these are, so what we are saying is we have L paths from 0 to L minus 1. The ith path is associated with attenuation AI and delay tau I, and therefore the resultant passband signal corresponding to the ith path is given as the real part of AI S of t minus tau I times e to the power of j 2 pi f c t minus tau I. All right. So these are the various signal components, passband signal components that are associated with the various paths. These are also known as the multipath components. These are also the various multipath components of the signal that are received at the receiver in this wireless channel. So we will stop this module here, and we will carry on with this analysis, that is modeling the received signal at the wireless receiver, in the subsequent module. Thank you.